Hello and welcome to lesson 4 of this unit. Today we're going to be looking at units of storage. So if you look here at 1.2.3, we're going to study all the different types of units of data storage here. We're going to look at how data needs to be converted into binary format to be processed by a computer. And we're going to look at data capacity and calculations of data capacity requirements. A computer stores data and instructions using electronic circuits inscribed onto computer chips. These circuits contain electronic switches made from tiny microscopic transistors. Each switch can be in one of two states, on or off. The two states are represented by the numbers 1 or 0. Computers represent all data and instructions using combinations of these ones and zeros. So it doesn't matter if we're talking about sound or text or graphics or movies, it all has to be represented just using ones and zeros. And then when we view or listen to this data, we need to take those ones and zeros and then convert that back into a human readable form. Binary is a number system that only uses two values, 1 and 0. So a bit is one binary digit, a 1 or a 0. So we've got binary digit, bit. That's where bit comes from. Not a lot of people know that. We often like to group these bits together. We have the nibble, which is 4 bits. 1001 would be an example. But more importantly, we have bytes, and that's a group of 8 bits, for example 1001101, the symbol for which is usually a capital B. I hope you get the little joke here, a little bit of coding humor. We've got bits, nibbles, and bytes. Spot a common theme there?
Does your dog bite? No. Oh. Nice dog. I thought you said your dog did not bite.
That is not my dog.
We also like to group bytes together in multiples of 1,000, what we call kilobytes. We then group these together in units of 1,000 and so on and so forth. So we talk about 1,000 bytes equals 1 kilobyte. 1,000 kilobytes equals 1 megabyte. 1,000 megabytes equals 1 gigabyte, etc. If you look over at this side here, you can see we've got different units of measurement. So we've got kilo for 1,000. We've got mega for 1,000,000. And you can see the difference between these numbers in terms of size. So if you look here, we've got a difference of 3 orders of magnitude between each unit. So we can convert between them by either multiplying by 1,000 or dividing by 1,000 as appropriate. Of course, the information on this slide isn't technically 100% correct. It's a simplified version. In reality, there aren't 1,000 bytes in a kilobyte. There are 1,024. Why is that? Well, this is a binary number system. It's a number system based on the number set 2. It's base 2, rather than the number system that we use in day-to-day life, which is based on multiples of 10. So if we start with 1 and work on multiples of 2, we get 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1,024. So that's why technically there's a 1,024 bytes in a kilobyte, 1,024 kilobytes in a megabyte, and so on. However, in your exam, you're going to have to convert between these units. And multiplying and dividing by 1,024 is quite complicated. So in the exam, you can just use multiples of 1,000. They're simplifying it a little bit just to make it easier for you to do all this calculation in your head. So in your exam, it's 1,000 bytes in a kilobytes. That will get you the marks. If you were to use 1,024, you would also get the marks, but working with units of 1,000 is a lot easier. Now, I think it's important to make sure that you can understand these units of measurement in the proper context. So a byte, for example, would be just a single text character, for example, the letter A. When we move on to kilobytes, we're talking about text files and small images. Megabytes would be the typical storage of a photograph that you take with your phone or with a digital camera. Also, MP3 music tracks would be measured in megabytes. For gigabytes, well, we typically measure high definition movies in gigabyte file sizes, and also modern video games often weigh in at several gigabytes each, especially the kind of latest AAA games. When we move on to terabytes, this is the unit of choice for hard disk drives. Most hard drives that are sold are 1 terabyte plus nowadays because they have to contain all our text files, all our photographs, all our games, and all our movies. So now we're looking at terabytes for hard drives. My first hard drive back in the day was 20 megabytes, so not suitable for today's standards. And then if you look at petabytes, well, petabytes are huge amounts of storage. What would use petabytes of storage? You're looking at data centers, servers, supercomputers. If you think about Google or Dropbox or Facebook, these are the kind of companies that would be using and storing petabytes of data. So let's do a little practice converting. First question here is, how many gigabytes are there in 2.1 terabytes? So if we have a look here, we're going from terabytes, which is here, to gigabytes, which is here. So we're going from terabytes to gigabytes. And we're going to do that by multiplying by 1,000. One jump is 1,000. So that's 2.1 times 1,000. We've got 2,100 gigabytes. Next question. How many bytes are there in 3.5 megabytes? Well, this time we're going to go from our megabytes here, and we're going to jump to kilobytes, which is a multiple of 1,000. And then we're going to jump to the next unit down, which would be bytes. And again, that is in multiples of 1,000, isn't it? So that's 2 jumps. So we're going to say, right, it's 3.5 megabytes times 1,000 will give us the answer in kilobytes, and times that answer by 1,000 to get the answer in bytes. Of course, 1,000 times 1,000 is just 1 million, isn't it? So I can just say 3.5 times a million, or 3.5 times 1,000 times 1,000, and that gets me 3,500,000 bytes. What happens if you go the opposite way? So next question, how many megabytes in 67 million bytes? So this time we are going from bytes, and then we're going to work out how many megabytes. So we're kind of going in the opposite direction, aren't we? This is in multiples of 1,000, but this time we're going to be dividing by 1,000 for each jump. So 67 million divided by 1,000 will give us the number of kilobytes. Divided by 1,000 again will give us the number of megabytes. And again, I could just simplify that and say, okay, 1,000 times 1,000 is a million, 67 million divided by a million, and that would give us 67 megabytes. It is important to be able to calculate the required data capacity when choosing storage media. To do this, typically we add up the estimated file size for each of the files we need to store, and then add around 10% to make allowances for small variations and metadata. Metadata is just data associated with a file, sometimes referred to as data about data. So for example, if you take a photograph, that photograph will contain all the pixels for the image, but it will also contain information such as when the picture was taken, perhaps where the picture was taken, and all this extra information that's stored along with the main image. So if we take a look at the example here, we can see I've got 10 pages of word processed documents at 100 kilobytes, so that's 1 megabyte in total, 3 postcard sized images at 6 megabytes, totaling 18 megabytes, 5 minutes of MPEG video at 50 megabytes each, 250 megabytes, for a total of 269 megabytes. Then to this, I'm going to add in about 10% for overheads and metadata. Okay, so that's what we've got here. And I'm going to just say that's roughly 27 megabytes. I'm rounding it. I could say 26.9 megabytes, but I'm just going to say 27. So 10% of roughly 270 megabytes is 27 megabytes. I'm going to add all that together to get a grand total of approximately 296 megabytes. Now, interestingly, for some exam specifications, you have to add that 10% or you're not going to get the answer right. For the J277 course from OCR, this is optional. You can choose to add the overhead, or maybe you don't. The answer that you give only has to be approximately correct. Of course, read the question carefully. If it asks you to add in 10% for metadata, please do so. But otherwise, you do have a bit of a choice. So in some of the examples coming up, sometimes I'm going to add metadata, sometimes I'm not. It's going to depend on the kind of data, and I'll explain why as I go through it. The format used to store these files can also make a significant difference to the size. For example, 137 characters of text stored in different formats can vary greatly in terms of size. So this is what I did this morning. I just wrote some random words into a text file, 137 characters in total, and then I saved it in 3 different formats. So you can see that the rich text format, the RTF format, comes to 43 kilobytes. The Word doc that we're mostly kind of familiar with comes to 12 kilobytes, and just as a plain TXT file, no formatting, no special data, that 137 characters became less than 1 kilobyte. So you can see how you choose to store the data, what format you're using, can make quite a significant difference. Let's take a look now in a bit more detail about how to calculate data capacity for lots of different types of data. I'm only going to concentrate on the calculations in this set of slides. In the next lesson, I'm going to go through text and images and audio in more detail and explain what all these different terms mean. But just for today, I'm just going to go through the calculations themselves. So calculating text size is quite easy. It's simply just the bits per character multiplied by the number of characters. So for example, a text file with 200 characters stored in 7-bit ASCII format, I'll explain ASCII in another lesson, comes to 7 times 200, which is 1,400 bits. I can divide that by 8 to simplify it and get to 175 bytes. So that's just how we calculate text size. Image file size is the color depth multiplied by the image height multiplied by the image width. The image height and the image width are both in pixels. So the number of pixels. And I'm not writing that very well, but you get the idea. So for example, a 16-bit image that is 2,000 pixels high and 800 pixels wide comes to 16 times 2,000 times 800 equals 25,600,000 bits. Now, we don't record the final answer in bits because that's not very convenient. I'm going to convert that into megabytes. So I divide by 8 to convert into bytes, divide by 1,000 to convert into kilobytes, and then divide by 1,000 again to convert to megabytes, or divide by 8, divide by a million, and we get 3.2 megabytes. Images often have a lot of associated metadata, so I'm going to add 10% for metadata and overheads to that. So that's 3.2 plus 0.32 equals 3.52 megabytes. Now I could also simplify that a little bit. I could round that and just say 3.5 megabytes. That would almost certainly be correct as well. Sound files, we have the sample rate in hertz multiplied by the duration in seconds multiplied by the bit depth multiplied by the number of channels. Now, number of channels means is it mono or stereo, 1 or 2 channels. So if we have a look here, I've got a sample of sound is made at 44.1 kilohertz for 1 minute at a bit depth of 16 bits. And let's just imagine this is mono or 1 channel, so I don't have to do any extra calculations here. First thing to know is, of course, it's kilohertz, so not hertz, so I have to change that into thousands, so that would be 44,100. So we get 44,100 times 16 times 60, because 1 minute is 60 seconds, and that gets us 42,336,000 bits. Again, I'm going to convert that to megabytes. Divide by 8, divide by a million, and we get 5.29 megabytes. Metadata is typically small for sound files. I'm just going to round that and say, okay, that's going to come to 5.3 megabytes. Again, that's mono. one channel. If the track were stereo, then I would then multiply that by 2 for the stereo 2 channels, and that would get me a total of approximately 10.6 megabytes. And that's how we would convert for sound files. So it is a little bit of math there, just read the question carefully. In summary, binary is a number system that uses two values, 1 and 0. There are various units of storage you need to know about. You need to know about bits, nibbles, and then most importantly, bytes, kilobytes, megabytes, gigabytes, terabytes, and petabytes. You have to remember the order. You have to be able to convert between these. It is also important to be able to calculate the required data capacity when choosing a storage media. Thank you very much for paying attention in this lesson. I'll be back with more in the future. Good luck and have a good day.